To motivate 3C, I want you to think about how we describe our age in pounds. We don't say that we are 21.45698 years old or 165.425788 pounds. Typically, we round these values to the nearest integer. In this section, we will discuss using significant digits, rounding, precision versus accuracy, and avoiding systematic errors when problem solving. Significant digits are the digits in a number that represent actual measurements and therefore have meaning. Non-zero digits are always significant. The significance of zeros will depend on the position of the non-zero numbers in a number. We will talk about this more in this video. In scientific experiments, there are two types of errors we will discuss. A systematic error occurs when there is a problem in the measurement system that affects all measurements. By identifying it, all of the measurements can be adjusted to eliminate it. Random errors are often out of the control of the researcher and inherently unpredictable. To minimize the effects of random errors, it is best to make many measurements and average them. By taking a large number of measurements and averaging them, this can minimize those random errors. Let's focus on significant digits. In your book, you will see a chart with these 5 important rows. Remember that non-zero digits in a number are always significant. Zeros that follow a non-zero digit and lie to the right of the decimal place, such as 4.20 or 3.00, these are always significant. Zeros between non-zero digits, such as 4002, the zeros lying between the 4 and 2, these are always significant. Now, zeros to the left of the first non-zero digit, because they're acting more as placeholders. Here we have 6 1,000ths. These are never significant. Zeros to the right of the last non-zero digit, but before the decimal place. Again, you're thinking about placeholders, 210, 40,000. The 4 here is significant. There's 4 zeros to the right of the 4 because they are between a 4 and a decimal place are not. These are not significant unless stated otherwise. The important things here to remember, in the first 2 rows, when we're talking about zeros, here the zeros are lying between non-zero digits, or they are to the right of non-zero digits, and because this 0.20 was left remaining here, this is probably signifying that it was rounded. It may have been something like 4.196, and so keep in mind these types, these are significant when the zeros have these 2 cases. If the zeros are acting more of a placeholder, 0.006 or 40,000, those zeros are not significant. Now we're going to review rounding a bit. If I have a number such as 324.5832, the nearest hundred is the hundreds place here, so the 3, where the 3 is located. I've underlined the 3 here. If I want to round to the nearest hundred, I identify the digit that is in the hundreds place. I look 1 digit to the right of that number. So here I have a 2 to the right of the 3, directly to the right of 3. If that number to the direct right of the hundreds digit is 5 or greater, then you round up, you increase the number by 1. Here, since 2 was less than 5, then we've rounded this to 300. So 324.5832 to the nearest hundreds is 300. When rounded to the nearest hundreds, this number has 1 significant digit. Recall, these zeros lay to the right of a non-zero digit, so therefore the zeros are not significant digits. The 3 is the only significant digit. To the nearest tens, we identify the tens place. I have a 2 here. Because the number directly to the right of the 2 is a 4, it is not 5 or greater, we leave this at 320. So 320 is this number rounded to the nearest tens. The number 320 has 2 significant digits. The 0, again, by the chart we looked at before, is not significant. 324.5832 rounded to the nearest integer would be 325. We see that the 4 is in the ones place. The 5 that is in the tens place, directly to the right of the 4, is a number that signifies increasing the ones place by 1. So 325 is this number rounded to the nearest integer. This number, of course, has 3 non-zero digits, so it has 3 significant digits. To the nearest tenth, we identify the tens place. That is the first place to the right of the decimal. Since I have a 5 there and an 8 directly to the right, I'm going to bump that 5 up so that I have 324.6. This 6 represents the tens place. If you think about symmetry, we have the 4 in the ones place. Tens is to the left of the 2. Tenths is to the right of the 4. This number has 4 non-zero digits. Therefore, this number has 4 significant digits. To the nearest hundredth, we identify the 8. The 3 does not tell us to bump that number up. Therefore, we've rounded this number to 324 and 58 hundredths. This number has 5 non-zero digits. Therefore, it has 5 significant digits. Please be careful when rounding in MyLab Math, since most of the homework is graded and created with a program, then often you need to double check that you are following their instructions for rounding. So please make sure that you recognize the difference between hundreds and hundredths. Okay, precision versus accuracy will be 2 keywords in this section. To remind you, this is directly from your book. Accuracy describes how closely a measurement approximates a true value. So an accurate measurement has a very small relative error. Precision is different. Precision describes the amount of detail in a measurement. So for random and systematic errors, we've discussed these a bit in the introduction to the video. Random errors often occur because of inherently unpredictable events in the measurement process. These are often out of our control. Every scientific experiment will encounter random errors. This is why it's often best to make multiple measurements. Systematic errors, however, are different. These occur often when there's a problem in the measurement system. It may make all of measurements perhaps higher than they should be or lower than they should be. Often you can recover systematic errors if you notice these after making those measurements, but sometimes these can be prevented. So in a really well-developed research experiment, it's most likely that these can be prevented by preparing your measurements carefully. In real-world mathematical modeling, it is unavoidable to encounter random errors. As an example, if we were to complete an educational research project to compare the effects of remote and in-person teaching, suppose that the scientists used 2 classes for this project. Now consider that 3 of the participants in one class were ill one day, so that they did not perform at their usual level. This would be an example of random error. This was out of the researcher's control. Now consider that one of the classes the scientists intended to use was at 7:30 a.m., but the second class was at 1 p.m. Now, in this planning, the scientists should have considered that a 7:30 a.m. class often has a lower average than a 1 p.m. class. Using these 2 classes to compare the effects of remote and in-person teaching would be an example of a systematic error. In the planning, things like this should be considered so that they don't create a larger difference in the outcomes between two groups. Another example of a systematic error would be if one of the classes was taught by a first-year teacher, whereas the other was taught by an award-winning instructor. We would expect the two classes to have different outcomes in this case as well. So this is another example of a systematic error. The absolute error will be equivalent to the measured value minus the true value. This is the simple difference between the measured and true values. The relative error, so relative taking into account other measurements, the relative error is that absolute error divided by the true value. This is often given as a percentage. So again, we take the measured value minus the true value, and this is all divided by the true value. Rules for operations. When rounding, if it is not specified, when you are working addition or subtraction problems, always round the answer to the same precision as the least precise number in the problem. If one weight was given as 125 pounds, whereas another weight was given as 33.25 pounds, we're going to use the least precise number. Though one had a 0.25 there, the other didn't. So we're going to round to the nearest integer there. So always round the sum or difference of a problem, round that to the same precision as the least precise number in the problem. When multiplying and division, if rounding is not specified, always round the final answer to the same number of significant digits as the measurement with the fewest significant digits. So for addition and subtraction, when rounding, we look for precision. For multiplication and division, when rounding, we look at significant digits. Always remember that you should wait to round until after completing all of the operations. Here are two examples. Here we have 5.5 times 10 to the 5th. Written out, this is 5.5, so I would move the decimal to the right 5 places. We're finding the sum here with 300. First, I add the two numbers. Since this is 550,000 plus 300, we have 550,000 and 300. Now, when adding and subtracting, we focus on precision. Since 300 was rounded to the hundredths place, whereas 5.5 times 10 to the 5th was rounded to the 10,000ths place, this is a less precise number. Therefore, we will round to the nearest 10,000ths place. The sum of these two numbers is approximately 550,000. The 300 was nearly, you might think of that as less significant, less precise. It was less precise. So therefore, we round this to the nearest 10,000 because the first number was less precise. When multiplying, focus on significant digits. Here we have 45 times 32.8. First, multiply these two numbers. Then we see that 45 had two significant digits, whereas 32.8 had 3. We must round the final answer so that it has two significant digits. Therefore, my rounded answer becomes 1,500. For addition and subtraction, again, look for precision. 108 plus 0.68 is approximately 109 because the first number was the least precise number in this sum. For division, think of division as the same as multiplication. Here I have 108 divided by 0.68. When dividing here, remember to round according to significant digits. The denominator in that quotient had only two significant digits. Therefore, we round the final answer so that it has two significant digits.